Hello and welcome to York Universe, the astronomy and astrophysics podcast, written and presented by the students, faculty, and alumni and friends of York University. You will now find us wherever podcasts are distributed. I'm Paul Mackin, one of your hosts this evening, and I'm joined by Suna Withers. We're broadcasting live from the Allan Carswell Observatory, located at the Keele campus of York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday at 9 p.m. local Toronto time. And we'll talk more about what that means in a minute, or currently at 1 a.m. Tuesday Universal Time at York U Observatory. We also run in concert with our online public viewing, or as we call it, the OPV feed run by the observatory staff. Tonight, we're going to be showing archival images because the weather's not great, but to navigate to our live show or find out more about us, please check out our website at yorku.ca/science/observatory and follow the link to our online public viewing chat on YouTube. Any questions or comments you may have on past shows or suggestions for future shows, please send us an email at observe@yorkuniversity.ca. You can also connect with us on Instagram with the handle at York U Observatory or on Facebook at Allan I. Carswell Ob. All of our programs are free, but if you feel like making a donation, and we'd certainly appreciate that, please visit our website at yorku.ca/science/observatory. We will be monitoring the YouTube chat for questions and post contents. So as I said, tonight's weather isn't looking great, and the domes are closed. So we will be showing archival images, but they're all captured by our telescopes. So let's get in. So before, I'd like to introduce my colleague, Suna. How are you doing tonight, Suna?
Oh, I'm good. How are you?
I'm fine, other than the fact that I'm just recovering from a cold. So every once in a while, I'm
Oh,
pausing to cough in the background. But
oh,
we were going to have the dome open tonight, but some storms came in, and when I was driving home, lightning in November in the GTA is very rare, and then there was
yeah.
hail coming, and there was hail coming down as well. So a little bit of a messy night. We're not observing, but what have you been up to? Have you been spending much time in the observatory lately?
Yeah, I've been spending a lot of time in the observatory, but we're starting to hit that, couple months of clouds and terrible weather, so I have a feeling that's not going to last,
No,
unfortunately.
you sort of drop down to one night in five or one night in four if you're really lucky come this time of year, and that
Mhm.
kind of goes from now till March. But you know, astronomy is all about weather watching. In fact, I just set up a weather station in my backyard observatory. So
Oh,
yeah, so hopefully that'll help me be able to predict things a little better and make sure I can maximize my observing time.
yeah,
Have
I
you?
love having the little weather station that we have on the observatory. It's a nice thing to just be able to kind of check in on while observing. So it must be
Yeah, it's
fun.
oh, it's great. Yeah, it's a very cool little instrument. But I had to check with my wife where to put it in the garden so it wouldn't diminish from the aesthetics of our garden. But I think we got there. Um, but interestingly, this morning when I woke up, it was not the same light as it was a couple of days ago. It was a little darker, and the reason for that, of course, is because we just had switch over from daylight savings time this past weekend, and I don't know how you feel about the clocks changing soon, but it's always driven me a little crazy.
Yeah, I agree.
Yeah, it's just it always takes me about the fall isn't so bad because you're sort of getting an extra hour's sleep, but you pay for it in the spring when you lose an hour. And NASA did a study uh, years ago when they talked about jet lag, and it takes longer than you would think to recover from jet lag. And if you ever travel to a place like the other side of the world, like I've been to Australia a few times, And it takes 2 weeks. If you go to Australia for 2 weeks, it's one of the most self-defeating things in the world because you're just getting over jet lag and then you have to come home. So
Oh
Australia is
no.
not a, if you're coming from Canada or North America, I guess, Australia is not a fun place to go if you're going for less than a month. But
Yeah. Yeah, I've never done a trip as extreme as Australia, but I have gone to places that have like a, like 7 or 8 hour time difference, and it takes a bit
it does. It
to.
really does. It really does. Yeah, it's harsh, and jet lag is to be taken seriously. But we're talking about this week in space history, and I did want to talk a little bit about daylight savings time, and there's some controversy about it that's coming to the fore now, which is probably worth discussing. So, interestingly, the very first proposal for um, daylight savings time came in 1874, and Benjamin Franklin, the American writer, scientist, he was a polymath, a natural scientist, a mathematician, uh, a philosopher. But he wrote a satirical letter suggesting that Parisians, he was also the US ambassador to France, that Parisians could save candles by waking up earlier to take advantage of sunlight. This is not considered a serious proposal for daylight savings time, but it was kind of the first recorded uh, proposal. Now, the modern origin, the modern concept was more seriously suggested by George Hudson, but he had kind of weird methods. He was an entomologist from New Zealand, and he wanted more evening daylight for his insect collection. He wanted to kind of get, he wanted to optimize his time so that he could get more insects and kill them and stick pins in them in little boxes. But the first national implementation was by Germany during the First World War, and it was to conserve fuel. And we'll talk more about this idea of conserving fuel. But the idea was basically you got people up and got them to bed earlier, got them up earlier, got them to bed kind of earlier, and they weren't using as much fuel during the day. They were relying more on sunlight. And then it got adopted by other countries, including the UK, and then the US adopted it soon after, with the US enacting the Standard Time Act of 1918, and Canada's in sync with that, which established both standard time zones, which was a Canadian invention, by the way, and daylight savings time. And then post World War One, the practice was unpopular in the U.S. and was repealed after the war. And President Woodrow Wilson vetoed the repeal, but it was so unpopular that Congress was able to get the necessary votes to override the veto. And then World War II came along and it was reinstated during World War II as wartime. After the war, individual states and cities could choose whether or not to observe daylight savings time, which it's interesting because in Canada, Saskatchewan doesn't have daylight savings time. And I think in states, Arizona doesn't. Uh, but there was some standardization with the Uniform Time Act of 1966, which standardized the practice in the U.S., requiring all observers to use it statewide. But there were some exceptions, but years later, year-line daylight saving times was implemented for a short period of time in the 1970s to address the 1970 kind of 4 to 6 energy crisis. It was unpopular, but later reversed. But again, every time there's an energy crisis, it's a very easy thing for, and I'm not being cynical about this, for politicians to say, well, let's extend daylight savings time. But interestingly, it doesn't really save any energy. Uh, Studies have shown that maybe 0.5% improvement. And given some of the changes we're now implementing in our energy infrastructure, uh, it doesn't save very much at all. In Canada, it saves even less because so much of Canada's power is based on hydroelectric, nuclear, renewables, and so on. So, the province of, if you take the province of Ontario, the province of Quebec, the province of Manitoba, the province of British Columbia, and New Brunswick, between those, you've got a huge amount of nuclear and um, hydroelectric. So we're not going to save any fuel with daylight savings time. And now there's, some thought to abandon the idea. Again, the energy savings are not particularly good. Medical experts are worried about the health impact. I'm not a medical expert, but I know that I certainly don't enjoy the experience, and I find it kind of discombobulating every time it happens, and so this is an ongoing debate. I don't know what would trigger something like this. The place I live in Canada, Ontario, we have a law which basically states that if the neighboring U.S. states abandon daylight savings time, and I think Quebec as well, will automatically abandon it as well. So we're waiting for a trigger mechanism to do that. But what about you? So do you think this is something we should get rid of?
Yeah, I'm really not a fan of daylight savings time or just kind of the time change in general. I really didn't know though that they had kind of a long history of a kind of debate about whether or not you do daylight savings and how you implement that. So it's pretty interesting to learn about. But yeah, the I'm not a huge fan of it. I do like the early sunsets. That's the part that I do like because we can go
Yeah.
observing and get basically quite a lot of data and quite a lot of images and still leave by like 10, 11 p.m. So I am definitely a fan of that. But in terms of the actual time change, I really wish we could just pick one and kind of stick with it.
Yeah, I find it weird. Like, one day it's getting dark around 6:30, and the next day it's getting dark around 5 o'clock type thing,
Hmm.
and I find that really weird. And then, as I said, in the morning, I'm an early riser, uh, so now the sunrise is coming earlier, and it just feels a little weird to me. And I remember when my daughter was uh, I don't know, probably about 7 years old, she and I did a little experiment where we charted uh, how much daylight there was every day. We went on a website, found out when sunrise was, when sunset was, and I had to explain to her the whole idea why it changed by 1 hour at this one point in the year, and I think she thought I was joking, and because it is kind of counterintuitive, but I mean, we're with it for now. But it is, again, I don't mean to seem cynical, but I remember during the last sort of energy crisis, the first place the U.S. Congress went to was, let's extend the daylight savings time, and really doesn't do anything
Hmm.
from an energy point of view, and even less so in a country like Canada, which is so not tied to renewables. Sorry, which is so tied to renewables or non-carbon based energy sources.
Hmm. Yeah, it just
But
kind of,
go ahead. Sorry,
I
Claire.
was just saying it's kind of on my end, it just gets a little bit annoying having to deal with the time change every year. It's you're probably a bit more affected by it because you said you were an early riser, but my sleep schedule is complete chaos most of the year. Um, but yeah, it can get just a little annoying and kind of catches me off guard when all of a sudden it's getting dark so early. And then on the other end,
Yeah.
when we switch back, then it starts getting dark so late all of a sudden. I'm really not a huge fan.
Yeah, no, it's I know your schedule a bit because you're in the observatory a lot. I mean, you're a creature of the night, but
Yeah.
but in an astronomical sense, not a macabre sense. But leaving Canada a bit, well, let's maybe head south down to Puerto Rico, and I'll turn this history item over to you.
Okay, so this is November 1st, 1963, which was when the Arecibo Observatory opened in Puerto Rico. Now, the Arecibo Observatory has come up actually pretty regularly on this show for the past few years, and I'll get to exactly why a little bit later on. But basically, the Arecibo Observatory was this really amazing radio telescope that was located in Puerto Rico. It was installed in basically this really big, massive natural sinkhole that I guess provided engineers with like the perfect place to build one of these massive radio telescopes. And unlike a lot of the radio telescopes that we see today, which are actually these big arrays of radio dishes that you can arrange to sort of work as one massive radio telescope, the Arecibo Observatory was just a single dish. It was a 305-meter diameter single dish radio telescope that sat in this sinkhole and basically pointed straight, looked straight overhead. It had this massive instrument platform that was then suspended above the observatory, which weighed about 900 tons, which could help the observatory kind of point to kind of whatever area that it was planning on looking at. But Arecibo was a completely revolutionary radio telescope for a lot of different reasons. And for around 50 or so years, it was actually the largest single dish radio telescope on the Earth. That changed in 2016 when China opened and started operating their telescope called FAST, the 500-meter aperture spherical telescope. That's what the FAST acronym stands for. And kind of like the name suggests, it was this 500-meter diameter radio telescope that beat out the size of Arecibo. But the Arecibo Observatory, if we go all the way back in its history to the 1960s, actually has a very interesting origin story, which is that it was only partly constructed to do science. One of the main reasons that the Arecibo Observatory was even constructed in the first place was so that the United States Department of Defense could use a radio telescope to detect incoming missiles to the United States. So for the first few years of Arecibo's lifetime, it was owned and operated by the Department of Defense. But then in 1969, the ownership transferred from the Department of Defense to the National Science Foundation, or NSF, which is also run by the United States government. And the NSF continued operating Arecibo until it was decommissioned in, I think it was 2020. And in terms of science, there were a couple of different things that the Arecibo Radio Observatory could do. One of the interesting science goals that Arecibo has is it was actually looking at the Earth's ionosphere. So this is a part of the Earth's upper atmosphere starting at around 80 kilometers altitude, where the atmosphere is being hit with so much radiation from the sun, so much high energy radiation, that all of the sort of things in that part of the atmosphere are ionized. So you don't have neutral gas like you do at lower altitudes, like the kind of gas that we breathe. It's all ionized gas at these altitudes. And because the gas is ionized, it actually has a lot of effects on things like radio communications, because it can interfere with radio waves. So astronomers and scientists, even people from the Department of Defense, did also want to understand the way that the ionosphere could affect those types of communications and long-range communication on the surface of the Earth. So Arecibo was this really interesting mix of a telescope where it just did a whole bunch of different things. It worked for the Department of Defense, it studied the ionosphere, and it also did a whole whack of observations and a whole lot of science in a bunch of different areas of astronomy. So there's a very, very long list of all of the things that Arecibo did, but I'm just going to talk about a couple of maybe, I guess, the highlights that Arecibo was able to accomplish during its lifetime. It was in, I'm not sure what year, but in 1993, the Nobel Prize in Physics was awarded to astronomers who had worked with Arecibo data. And in this case, Arecibo had observed what's called a binary pulsar. And a pulsar is basically just a neutron star that is spinning very, very fast. Neutron stars are the remnants of massive stars when they die. They die in these supernova explosions called type 2 supernova explosions, and they leave behind a very, very dense core called a neutron star. Sometimes those neutron stars can be spinning very fast, in which case they're called pulsars. And Arecibo observed a binary pulsar, which had a companion when with the pulsar orbiting the companion, the two of them were orbiting each other, which was then used to confirm predictions from Einstein's general relativity, which described the way that gravity works in very extreme situations and very normal situations as well. So it was used in 1993 to be awarded the Nobel Prize to astronomers working with Arecibo data. On the topic of pulsars, it was also used to discover the first millisecond pulsar, which are really crazy types of pulsars that rotate in matters of milliseconds. Now, keep in mind, these pulsars are absolutely massive. They're not tiny little things in space. They're actually very large objects, very massive objects as well, that are rotating once every millisecond or less, hence the name millisecond pulsars. Arecibo was also used to discover the first exoplanet in 1992, which was found orbiting a pulsar. It was used to study things in our solar system as well. This included near-Earth asteroids and also created really nice maps of the surface of Venus. Now, anybody that's ever observed Venus before or seen pictures of Venus in visible wavelengths that we can see will know that you actually can't see the surface. Venus has a very thick carbon dioxide atmosphere with lots of clouds that completely blur the surface to us. So if we want to actually observe the surface of Venus, we have to go to other wavelengths of light, including the radio wavelengths that the Arecibo Observatory was able to see. So it also mapped the surface of Venus and even observed the planet Mercury, discovering that it has a very weird orbital resonance, a 2 to 3 resonance, which means that for every 2 orbits Mercury makes around the sun, it rotates on its axis 3 times. And one of the really cool things about this orbital resonance is that Newtonian gravity can be used to describe pretty much everything that we see in our solar system, because these are sort of classical examples of gravity. So general relativity can absolutely describe those situations as well, but you can also use the Newtonian version of gravity to describe that. But the orbital resonance of Mercury is so odd that you actually need general relativity to describe it. So Arecibo actually did a whole lot of observing that confirmed Einstein's general relativity and was able to see general relativity's predictions in action. The also a cool thing to mention is that if anybody has seen the movie Goldeneye, Arecibo made an appearance in that movie. I have not seen Goldeneye, so I don't know exactly what scene Arecibo made an appearance in, but you can catch a glimpse of the Arecibo Observatory in that movie. Now, the reason that Arecibo had been discussed on this show kind of more recently was because tragedy struck in around 2020 at the Arecibo Observatory. There had been a series of hurricanes and I think also earthquakes that had hit Puerto Rico in the years before 2020, which had kind of done increasing amounts of damage to the observatory. In particular, they did damage to some of the cabling systems that held up that 900-ton instrument platform that was sitting above the Arecibo dish. There had been plans to repair some of these cables. There had actually been cables and components that had been shipped out to Arecibo from the United States to repair them. But unfortunately, they weren't done on time because in around November and December of 2020, the issue started to become a lot more serious. Multiple cables had snapped. They had become very structurally compromised. And I think I remember it actually got to a point where the NSF, who was running Arecibo, decided that it was too risky to even try and repair some of these cables. There was too much of a risk that something could go wrong and somebody could get hurt in the process. So they had decided to decommission the Arecibo Observatory in sort of a nice, regulated way. But before that could happen, on December 1st, 2020, the third cord or one of those cables kind of reached the end of its rope. It snapped, and this massive 900-ton platform just came crashing down onto the dish. It ripped a big hole straight through the dish of the Arecibo Observatory, which pretty much sealed its fate at that point. There was really no way that they could try to fix that. They would basically just have to replace the entire telescope, and they didn't have the funding for that. So the Arecibo Observatory kind of met its end on December 1st, 2020. And there is actually video of this cable snapping. It's kind of sad to watch, but there was a drone flying nearby that just caught the cable snapping, and you see the platform kind of just fall right onto the dish. Now, today, Arecibo has not been replaced with a new radio telescope. It's very likely not going to be replaced with a new radio telescope, unfortunately. But the NSF did put out a call for proposals to some people in the community to see how they could continue to use Arecibo, the land, and also the outreach center that Arecibo had while it was in operation. And they've come up with a plan that's called Arecibo C3, which is intended to keep using the Arecibo Observatory and that area as a place for education and outreach for science. So while it won't necessarily be focusing on astronomy and space sciences anymore, it will still be part of the community in Puerto Rico and hopefully used to inspire future scientists.
That's incredible, and actually, it's been in another movie as well, Contact, starring Jodie Foster. It
Okay.
appeared in that movie as well, and of course, Contact was written by Carl Sagan, and it's about basically the search for extraterrestrial life, the SETI project.
Mm.
Interestingly, that it was also Arecibo was also used by Drake, I believe, to do the first interstellar broadcast from Earth. Something he
Mhm.
got in trouble for. So.
Yeah, was that the message towards Messier 13?
Yes, it was.
Yeah.
Yeah. Yeah.
Yeah. Yeah, that
So
was yeah, the Arecibo message of 1974.
right, and yeah, Drake broadcast it out, and it was only it was only afterwards someone said, "You just told them where we live." So yeah, that's your message right there. Yeah, it's so it was he Drake didn't Drake got in trouble.
Yeah, so
Didn't
that's the
stop.
classic, it's the classic
Yeah,
ask for forgiveness, not permission.
I built a career on that. Uh, but on November 22nd, 1985, talking about building a career, uh, astronomer Harlow Shapley was born, who served as the head of Harvard College Observatory from 1921 to 1952. And he was also a political activist later in life. Um, Shapley used Cepheid variable stars to estimate the size of the Milky Way galaxy and the sun's position within it. In 1953, he also proposed the idea of a liquid water belt. It was a theory of his, which is now actually that idea has been taken and turned into the idea of what is called the habitable zone, which is basically you look for a part of a star, the part of the region around a star where a planet can exist and the temperature is okay for liquid water at its surface. Earth, uh, Earth and Venus, and maybe and probably Mars, all kind of occupy the habitable zone around the sun. Interestingly, though, the habitable zone doesn't necessarily mean habitable. And anyone who's ever looked at Venus knows it isn't habitable. And certainly Mars isn't right now either. So it's just a guideline for the part of a solar system where you might have conditions that could lead to a habitable planet. And this is one of the things that we're looking for with exoplanets. Um, Shapley also participated in the great debate with Herbert Curtis on the nature of nebulas and galaxies and the size of the universe. The debate took place on April 26th, 1920, which interestingly was the date I just realized reading this that was the day my grandmother was born, the exact day, in the hall of the United States National Academy of Sciences in Washington, D.C. Shapley took the side that spiral nebula, which we call galaxies, are inside our galaxy, while Curtis took the side of spiral nebula as island universes far outside our galaxy, and they were comparable in size and nature to the Milky Way. This issue and debate are the start of what we now call extragalactic astronomy, uh, while the detailed arguments and data, often with ambiguities, started to appear in 1921. Now, this led to a big battle, I suppose. Shapley was also very much opposed to the ideas of Edwin Hubble, um, uh, because Hubble also looked for the evidence that the galaxies were outside of the Milky Way. So Shapley fiercely criticized Hubble's work and regarded it as junk science. However, and this is a very good thing about science. Um, Shapley got a note from Hubble showing Hubble's observed light curve of V1, a Cepheid variable star in the Andromeda galaxy. Cepheid variables are standard candles. Their luminosity and their period are linked. So you can look at one and see how fast it's moving up and down and how bright it is, and you can figure out how far away you are from it. So this definitely showed us that the Andromeda galaxy was outside of our galaxy. And that was a big deal. So he reportedly told a colleague at that time, here is the letter that destroyed my universe. But he also encouraged Hubble to write a paper for a joint meeting of the the American Astronomical Society and the American Association for the Advancement of Science. Hubble's findings went on to fundamentally reshape the scientific view of the universe, and Shapley accepted that. Despite having strongly argued against the idea of galaxies outside of the Milky Way, he went on to make significant progress in research on the distribution of galaxies, working between 1925 and 1932. In this time period, with the Harvard College Observatory, he worked to map 76,000 galaxies, one of the first astronomers to believe in evidence of galaxy superclusters. Because we're in a cluster of three galaxies, plus some smaller galaxies. Uh, but that's part of a bigger cluster, the Virgo supercluster. He was one of the people to actually put together evidence of that. Shapley later discovered a large and distant example, which is named the Shapley supercluster in his honor. He estimated the distance to the supercluster at 231 megaparsecs. A parsec is 3.25 light years roughly, and so this would be about 700 million light years away. It's pretty far, which is within 15% of the currently accepted value. In 1940, and this ties back to something you were just talking about, Suna, with Arecibo, Shapley helped found a bunch of government-funded science organizations, including the National Science Foundation, which took ownership of Arecibo. He shares credit with British biochemist Joseph Needham for the addition of S in UNESCO, which stands for the United Nations Educational, Scientific, and Cultural Organization. And he died shortly before his 87th birthday in a nursing home in Boulder, Colorado. So well done, Professor Shapley. You showed the noble side of science, and you used information produced by your colleagues to further expand our understanding of the universe.
Yeah, I really love talking about the great debate and how astronomers sort of started to realize that the universe has so many galaxies in it, because I want to point out the timeline here that this was in 1921. So this was like 100 years ago that this happened, which is not really that long ago in the grand scheme of things. So it's pretty interesting. It's kind of like you're looking at like an entire subfield of astronomy that was kind of born less than 100 years ago.
Absolutely, absolutely. And you and I have talked in a previous show that we hosted that, I mean, part of the problem here was Hubble wasn't the most approachable person. He was very difficult. And I think that you look at Shapley and he handled this with he was wrong. He acknowledged he was wrong. He was doing his job by defending his ideas, but at the same time, once it was shown, he showed that he was wrong. He showed great grace, adopted the ideas, and went on to extend the meaning of them. Very admirable, and this is typical of science. Science, you know, if you really, what changes ideas in science is better science.
Hmm.
You know, and this is a textbook example of that if you're looking at it from a history of science point of view. And you're right, it was only 100 years ago that in that period, the Great Debate, our very nature of our understanding of reality changed.
Hmm.
So it's fascinating. But
Yeah.
Suna, we're getting clear near halftime. Why don't you maybe quickly get through the next item and then we'll do our halftime announcement.
Yeah, sure. So this is going back to 1572 on November 2nd, which was when a supernova, a Type 1a supernova happened in the direction of the constellation Cassiopeia, which was now known as Tycho's nova, but officially cataloged as SN 1572. So, if you think about the night sky, one day in November of 1572, astronomers and many other people started to notice a new star appear in the night sky. It changed in brightness over time as these supernova explosions do. And at a certain point, it had a magnitude of -4. Now, astronomers use sort of weird conventions for the way we describe how bright something is. One of the ways we do that is using the magnitude system, where smaller numbers mean that something is brighter. So, a magnitude of -4 is ridiculously bright. It's about as bright as Venus is, if you've ever observed Venus. And it's even as bright, it's so bright it can actually be observed during the day. So this new star that appeared in the sky in 1572 would have been the brightest thing in the night sky next to the full moon, potentially Venus, depending on exactly what day you were looking at. Now, it was 1572, so nobody really knew exactly what this thing was. All that astronomers knew is that there was this new star that appeared in the sky that nobody had ever seen before. And various astronomers, including Tycho Brahe, took extensive observations of this star to try to figure out kind of what it was and what was going on. And the existence of this star and the work that Tycho Brahe did observing this star is also another way that our understanding of the universe changed over time, because originally astronomers didn't really know how static the universe was. They didn't really know that the universe could actually change, and it was this very dynamic place where new things could appear in our sky and then disappear. So when astronomers started observing this star, when Tycho Brahe started writing papers on this star, comparing his notes with other astronomers, it was really kind of a turning point for a lot of astronomers, because they now started to understand that things can exist outside of our solar system, very, very far away from us, and these things can change over time. Tycho supernova in particular had exploded on November 2nd, but it was first sort of noticed and observed by Tycho Brahe on November 11th, as it was going through this series of, getting brighter and brighter over time, until it eventually reached its peak brightness on November 16th, after which it started to dim. It continued to be visible to the naked eye for, I think it was a couple of months after, or maybe a full year later, actually. Um, it's visible to the naked eye, kind of until it eventually started to dim and became too faint for us to see with the naked eye. And this is why it's actually called Tycho's Nova, was because Tycho Brahe published a series of papers on this new star. The first one titled Concerning the Star, New and Never Before Seen in the Life or Memory of Anyone, which was then later reprinted the next year in 1573, after he compared his observations with those of other astronomers in other locations, which is why it earned the name Tycho's Nova. Now, this is one of the really interesting This Week in History items because it's not only a November 2nd, 1572 history item, but the debate about what exactly this new star was actually extended all the way up until 2008. Prior to 2008, in 1954, astronomers came up with a formal definition for a Type 1a supernova, which it turns out is what SN 1572 actually is. And in the case of a Type 1a supernova, what happens is that the remnant of a sun-like star called a white dwarf ends up orbiting very closely to another star that still has fusion happening somewhere in its core or in the outer layers. And what can happen in this case is that the white dwarf star gets too close to the other star and it starts to kind of siphon gas off of that star onto the white dwarf. This is all well and fine up until the white dwarf hits a mass of 1.44 times the mass of the sun. Because of the type of physics that's going on within white dwarfs, they cannot ever be heavier than 1.44 times the mass of the sun. So when you reach that point, the white dwarf explodes in a Type 1a supernova and leaves behind a denser neutron star at its core in place of the white dwarf star. So that definition was sort of formalized in 1954, after which various astronomers started to kind of theorize that Tycho's nova was actually a Type 1a supernova. But that wasn't sort of settled until 2008, after a series of follow-up observations with different telescopes were able to sort of make the final call that Tycho's nova was a Type 1a supernova. Now, Tycho's nova is actually still visible to the naked eye, it's not visible to the naked eye today, but it is still visible if you use strong enough telescopes. It's visible in optical wavelengths, radio wavelengths, and even X-ray, which are mainly just emanating from the gas from that explosion. And if you wanted to, you can actually take a picture of Tycho's nova. There's been a bunch of people who do it. It's a really pretty nova to actually look at. And one of the interesting things is it is slightly changing over time. Because of the type of supernova it is, that gas got ejected outwards into space, all of that gas is continuing to move away from the location of the explosion. And it's doing so at a rate of around 11 to 12% a year in radio and X-ray wavelengths. So while we do know that this Tycho's nova is existing today, it's probably not going to be recognizable in quite a bit of time, where all of that gas will kind of have faded and continued to move further and further away from the location of Tycho's nova until it eventually kind of just dissipates and we can't see it anymore. So this was a really interesting kind of event in history for a couple of different reasons, including the fact that this is one of only a handful of supernova explosions that humans have recorded from within the Milky Way galaxy. If you take some of these wide field telescopes and you point them at the sky, one of the things you notice is that there's actually a lot of supernovas that go off in the universe. You pick up a ton of them over time, but all of these supernovas are happening in other galaxies. So they're not that common within our own Milky Way galaxy at this point in time, and this is one of the few instances where something like this was recorded.
It's I've actually taken a look at the remnant. You're right; it's quite pretty. It's quite reminiscent of a lot of planetary nebula.
Hmm.
SN 1572. It's pretty. I mean, planetary nebula are often pretty,
Hmm.
but we have to get to our reminders. We're way past halfway through the show, so you are listening to York Universe. We're broadcasting live from the Allan I. Carswell Observatory at York University in Toronto, Ontario, Canada. Please look at our website, yorku.ca/sciences/observatory, to join the chat if you have any questions or want to see some of our content. Tonight, you're listening to myself, Paul Mackin, and Suna Withers. We have been discussing some historical items. If you're interested in our online public view, just navigate to our website and follow the links to join that fun. Suna, you want to tell us about our observatory tours? It's that shake-up time.
Yeah, so for most of the summer, we've been doing a mix of atrium tours, which are out on the top of the Arboretum parking garage. We have our 40 centimeter telescope up there and a couple of smaller telescopes as well. We've been kind of mixing those in with observatory tours where you can actually come to the observatory itself, see the 60 centimeter and 1 meter telescopes. It is officially too cold and too going to be soon too snowy to be doing the atrium tours anymore. So for the rest of the season, we have transitioned to only observatory tours. Most of the time, these tours happen weekly, but we will not be hosting an observatory tour this week on Wednesday. If you would like to plan to visit the observatory, please just visit our website. We have the upcoming schedule of tours on the front page of our website, and you can get tickets on Zephy on our Zephy page to come see both of the telescopes at the observatory. So please come by. We'd love to have you, show you the telescopes. And if it's clear out, we do open the dome up and do some observing with the 1 meter, which is always fun.
That's great. So yeah, the tours are a lot of fun, and uh, to get into items in the news, the other week, I'm originally from Wales. I grew up in a city called Cardiff, which is the biggest city in Wales. And the other week, I got a note on social media from one of my cousins, Richard, who was laid up with a minor health problem and had stuck in bed for a couple of days. And he said, "Hey, Paul, you're my astronomy expert. What's going on with this Three-Eye Atlas comet? The stuff I'm hearing about it is all crazy and stuff." So we have some news about a Three-Eye Atlas. Uh, Still no spacecraft. Still no spacecraft. That's not going to happen. But Three-Eye Atlas has brightened dramatically as it swims past the sun. So we're now at the time where Three-Eye Atlas is getting as close to the sun as it's going to get, which is about 1 1/3 times as far away as the Earth is from the sun. So it's still pretty far out. Now, we understand comets in our solar system reasonably well, but we don't really understand comets from outside our solar system. They grew up in different parts of the galaxy. The gas mix was probably different where they formed. They've got a history. They've been exposed to basically galactic vacuum as opposed to regular solar wind. So that their environment is very different. So we don't really know what to expect from an interstellar comet, and we've had three of them, and they've each behaved differently, but they each probably came from, in fact, they undoubtedly came from different places. So, it's been brightening, Three-Eye Atlas has been brightening more rapidly than expected. It sort of got, close, and then started to brighten faster than expected. And the way we can look at it, because it's behind the sun from our point of view, we're using solar monitoring satellites to look at it, and they can sort of see, a little bit behind the sun. So we're using things like Stereo A, SOHO, and GOES 19, and it's capturing what is really kind of a dramatic change in the comet. Between mid-September and late October, as it closed in from about 2 times the Earth-Sun distance to its closest approach at 1.36, it brightened dramatically. Its brightness increased proportionally to the inverse of the heliocentric distance. So the closer it gets, the brighter it gets, by a power of 7.5, which is significantly steeper than other comets we've observed, or when it was further out. Most comets brighten quite gradually as they get close. This one brightened quickly, at twice the normal rate. The observations also appear, it's distinctly bluer in the sunlight, which is a telltale sign that gases, rather than just dust, are continuing, are providing a lot of the visible brightness reflected, sunlight reflected in gases. Earlier observations found the comet dust was to be reddish, and this making this blue shift quite noteworthy. The research suspected emissions from molecules like cyanogen and possibly ammonia are responsible for this coloring. We can tell a lot about something's composition from the color it emits. Image from GOES 19's chronograph realized the comet showed the comet as an extended object with a visible atmosphere, what we call a coma, stretching about 4 arc minutes across the sky. So a big tail, a glowing envelope of gas and dust around the nucleus confirms that it's actively shedding material as it's heated by the sun. The perihelion, the closest point, was on October 29th. But again, I want to point out that this is comet-like behavior. It's just different comet-like behavior. And we don't have that many examples of what an interstellar comet should look like. So I don't know, Suna, if you've ever read Rendezvous with Rama, but this isn't Rama.
No, I've never read that.
You should.
Yeah, Three Eye Atlas has just been a really awesome thing. I always love these
Yeah,
weird interstellar comets that sort of pop up every now and then, or just the interstellar visitors in general. It's really crazy that we can actually determine the origins of some of these objects that we know they're not from our solar system. It's such an exciting thing to be able to do.
it is that. And, as new technology such as the Vera Rubin the Vera Rubin telescope come online, the Vera Rubin Observatory, we're going to be seeing a lot more of
Hmm.
these. Right now, it's not like there are suddenly a lot of, there's not suddenly interstellar comets. There have always been interstellar comets. Our ability to detect them and analyze them is new.
Hmm. Yeah, because
So
comets, or
yeah, go ahead.
no, I was just going to say, like, comets provide us even such a good way of studying, like, the history of our solar system. So you were mentioning with Vera Rubin, we're going to be start to see tons more of these things. So yeah, we're going to be able to actually learn about some of the history of other solar systems this way, which is just crazy.
Absolutely.
Yeah.
So talking about, I mentioned Vera Rubin, but you're going to talk to us about the JWST a little bit.
Yeah,
So
my favorite telescope, or one of my favorite telescopes. Um, So, of course, I talk a lot about JWST, especially in terms of galaxies, because JWST has been doing a whole lot of really interesting science for galaxies in the early universe. Prior to Webb, we didn't really have a very good idea of what normal galaxies in the early universe looked like. So, this is kind of a time where the universe was about a few hundred million to about 3 billion years old. Now, the universe today is 13.8 billion years old, so it's a pretty old universe at this point. And the earlier galaxies that we were observing with JWST are really giving us a look at what the galaxies just after the universe formed and within the first couple billion years were looking like, when galaxies were really starting to first form, get their structure, and start to influence their surroundings. So it's a very interesting sort of epic in the history of our universe to be observing, just because we can actually understand the early stages of galaxy formation and evolution. And one of the things that JWST has shown us is that galaxies in the early universe are a hot mess. That's according to a space.com article that they use the term hot mess for galaxies in the early universe. And honestly, it is pretty accurate. While galaxies today are very ordered, in the sense that all of their stars are sort of moving in the same direction in an ordered way with structure around the center of a galaxy, the galaxies that exist in the early universe are a lot smaller, so they don't really have a lot of that structure. And they're also in environments that are very different to what we're seeing today. So they were actually in these environments that had a whole lot of gas that surrounded these galaxies, that was constantly being pulled into these galaxies by the gravity of that galaxy and their stars. And when that happens, you just get complete disordered chaos. You have gas that's moving in every which direction around this galaxy. This is igniting very sort of clumps of star formation in different parts of the galaxy, where you have certain regions that are just going absolutely nuts, lighting up like a Christmas tree almost, forming tons of stars in very short periods of time. At the same time, you also have black holes that are appearing in these galaxies that are being fed by this gas coming from around these galaxies and is making them also kind of light up in their own way. Now, when this happens, all of these sort of these young stars and these black holes also start to emit a lot of like high energy light. They also start to kind of throw around gas and influence the stuff that's near them. In terms of stars, this is also something that we're familiar with on Earth. If anybody has ever seen the Northern Lights or aurora, this is a result of our sun actually flinging whole whacks of charged particles at us, and those particles then interact with our magnetic field and our atmosphere and lead to these beautiful aurora. The same thing happens with these other younger stars, but to a much more extreme degree, where they're really just throwing around a lot of gas and a lot of high energy light that's then sort of messing up and disturbing all of that gas that surrounds them, eventually forcing star formation to kind of quiet down for a little bit until you wait long enough and more gas starts to fall into the galaxy and ignite more star formation. So you really end up with a sort of cycle in these galaxies where they go through these bursts of like intense star formation, which astronomers have been calling bursty star formation. Sometimes this only happens in a specific part of the galaxy. So you just end up with galaxies kind of throwing gas every which way and in this completely and utterly chaotic state. But the astronomers that did this study, which they did by analyzing how gas in galaxies moves around the galaxy, had actually observed some galaxies, even in the process of becoming less of a hot mess and kind of settling down a little bit, where they actually did start to form a bit of structure, and they're now kind of becoming a bit more ordered galaxies. So really what we're seeing in these galaxies here are the sort of early stages of galaxies actually forming. And all of these galaxies would have eventually led or kind of gone on to be massive galaxies, very similar to the Milky Way and Andromeda and some of the more massive galaxies that we see today. So I think this was a really interesting study where we got to see a whole bunch of really see the pure chaos that happens within some of these galaxies and how crazy early galaxies are.
It's remarkable to me that you know telescopes. Well, any telescope is a time machine. It'll take you
Hmm.
back a little distance. It'll take you back a really far, far way back in time. But with James Webb, we're looking at the very earliest galaxies formed. And if you think about that, that is just, I mean, just even thinking about, just even saying it takes my breath away. We're going all the way back to shortly, as far as we can go with JWST, back to the very early behavior of our universe. We don't know what happened before that, but there is a period where we can't see back. But this is telling us a huge amount about where we came from, and to me that's incredibly fascinating. And I know this is work that you do. This is you soon work on exactly these sort of questions with the James Webb team, which is fascinating.
Yeah, it really is an amazing thing to be able to do to kind of look at some of the first galaxies that existed in our universe, and especially kind of thinking about the way that these can sort of shape the universe around them. Because these galaxies don't exist in isolation. They're constantly interacting with other things, the gas that's around them, other nearby galaxies. So it's always a really interesting thing to see what these early galaxies look like and kind of what they're doing and how they shape the things around them.
It's amazing. It is absolutely incredible. But I noticed, and I could talk about any number of these topics all night, but I noticed that we're now coming up on time. So I think it's time to move into our closing remarks. So uh, we're going to close up our telescope broadcasting for this evening, or our astronomy broadcasting for this evening. And I want to say thank you for joining us. You've been listening to York Universe, the Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Suna Withers and myself. And Suna's one of my favorite people to present with. We've done this a few times. The podcast and past episodes are available wherever podcasts are distributed. You can also connect with us on Instagram with the handle at Yorkview Observatory, or on Facebook at Allan I Carswell Obs. Our website is yorkview.ca/science/observatory. And there you'll find we have tons of interesting content. And if you feel so inclined, it's a great place to make a Canadian tax-deductible donation to our student-operated, not-for-profit observatory. So I want to say thank you for tuning in this evening. I want to wish my cousin Richard, who sent out that great question, a get well wish, and we wish you clear skies and good night. Thank you so much.
Have a good night.